This page of notes is about writing equations for exponential and linear functions. The first thing that we want to recognize is that an exponential function that does not have a horizontal or a vertical shift will have the form f of x equals c times a to the x. You'll notice that the h and the k are missing from this form because, again, there's no horizontal or vertical shift, so the h and the k would be 0, 0. So in this form, what we're going to recognize is that a is our common ratio. So if we're given a graph, we can write the equation for this function by finding consecutive ordered pairs. So when we look at our graph, what we're going to notice is that we have this point right here. That's the point 0, 3. We also have the point that's 1, 12. We need to make sure that when we're choosing our two ordered pairs that the y values are consecutive. So you can write yourself a note that you must use consecutive y values. If you don't use consecutive y values, then your equation is going to be off, your ratio is going to be off. So what we're going to do in this example is we're going to develop the equation of for the exponential, and then we're also going to use that to help us understand a faster way to do it when it's available. So first what we're going to do is we're going to find our ratio, and we're going to take the two y values and we're going to divide them. 12 over 3. And you have to do the second point over the first. So when we're reading our graph from left to right, the second point would be the one that's farther to the right. So we reduce that and we get 4. Then we can take that ratio and plug it into our standard form that we have up above. So we'll have y equals c times our ratio of 4 to the x power. Using either one of our points, that's a nice xy pair, we can substitute in for x and y. So I put 3 in for my y. I have my c times my 4, and my x is 0. Since I know that 4 to the 0 is 1, I can easily rewrite this equation. So I have c times 1, in other words, c is 3. Notice that by going through this exercise, we were able to find that not only our c value, but the c value did in fact turn out to be the y-intercept. So again, we can write ourselves a note to remember that c is the y-intercept. That'll be useful when we go down below and we're working from a t-chart. Now we're just going to take our c value and our ratio and put it together and write our final equation. This next section summarizes several things that you've already seen in the past. First of all, linear functions will increase or decrease by a common difference. In other words, each term is found by adding the previous term and the common difference. We typically write those in our slope-intercept form. From your Algebra 2 classes, you would have remembered or seen this before as an arithmetic series. Exponential functions increase or decrease by a common ratio, as we just saw up above. Each term is found by multiplying the previous term in the common ratio. As we saw up above, our standard form is going to look like this: y equals c times a to the x. In your Algebra 2 classes, you would have often referred to this as a geometric sequence or series. So the next thing that we want to be able to do is be able to look at a table of values and determine what type of function that we have. It's possible it's linear, it's possible it's exponential, and it's also possible that it's neither of those. In order to determine what type you have, what we're going to look at is how do we move from one y value to the next. So in example A here, I notice that to move from one term to the next, I simply subtract 3 each time. So if I'm subtracting 3 each time, this problem has a common difference. Therefore, we say that this one is linear. So when we go to write our equation for this in its nice slope-intercept form, what we should see is that our table of values automatically gives us our intercept. So we can simply write our equation. That common difference becomes the slope, and then we know our y-intercept is 2. So again, m is going to be our common difference. And this, of course, is our y-intercept. In the exact same way it was y-intercept in Algebra 1. On our next table, I notice that to move from 32 to 16, I am going to multiply the 32 by a half. To move from 16 to 8, I'm going to multiply the 16 by a half. And I can see that that pattern continues throughout the entire table. This one, therefore, has a common ratio. Therefore, we say this is exponential. So we could go through the exercise that we did up above and actually solving for the c value, but what we saw up above is that the c value turns out to be the y-intercept. So more quickly, we can grab our y-intercept of 16. We've already identified our common ratio is 1/2, and we simply raise that to the x power. Remember, c is the y-intercept. The 1/2, the a value, is the common ratio. And that's going to be your fast way to do that from a table of values. On our last one, what I notice is that to move, I could look at it from a linear perspective and see that I'm adding 2. But on the next one, I'm going to add 3. And on the next one, I'm going to add 4. So I can immediately see that this is not going to be linear. I can go ahead and I can check and see if potentially it's geometric. So I could do 4 divided by 2, and I would get 2. 7 divided by 4, and get 7/4. And immediately I see that this is not geometric. There is no common ratio or difference. Therefore, we simply say this is neither. And although it might be possible to write an equation for this sequence, that is not something that we will be doing in this class.